This video is part 2 on transformations. I'm going to show you vertical stretching and shrinking. Then we're going to summarize all the different transformations we discussed. And then we'll do 6 problems to practice. So let's go ahead and get started. I've already graphed f of x equals x squared. This is one of the functions we should be familiar with. And so what happens if we graph g of x equals 2 times x squared? So I'm going to go ahead and make a table of values, and I'll choose the same x values. If x is 0, 0 squared is 0 times 2 is 0. If we plug in 1, g of 1 will equal 2 times 1 squared. Notice you have to square before you multiply by order of operations. So this is 2 times 1, and you get 2. If you plug in 2, it'll be 2 times 2 squared, and that's 2 times 4, which gives you 8. If you plug in negative 1, you get 2. If you plug in negative 2, you get 8. And you can verify that on your own. So let me go ahead and graph this. Let's see how the graph compares to the original. So notice it's a more narrow-looking graph. If you look at each of my points other than 0, 0, you can see the y values have doubled. And so it's what we call a vertical stretch. The graph is basically stretching vertically twice as much. At each point, the y value is twice as big. All right, so let's see what happens. We call this a vertical stretch. And since it's 2 that we're multiplying by, sometimes people say by a factor of 2. A vertical stretch by a factor of 2. Let's go ahead and move on to C. Actually, let me label this. All right, so let's move on to C here. We'll do the same thing. If you plug in 0, you're going to get 0 again. If you plug in 1, notice we'll have 1/2 times 1 squared. Well, that's going to be 1/2 times 1, which is a half. And so we get a half there. Let's go ahead and plug in 2. When we plug in 2, we get 1/2 times 2 squared, or 1/2 of 4, which is 2. Similarly, if you plug in negative 1 or negative 2, you get the same, similar outputs. Basically, if you plug in a positive or a negative of the same number, you're going to get the same output because you're squaring that value. So let's go ahead and graph these points. And we draw the graph. And so this is H. And notice this time, each of these points has a y value that's 1/2 what it was originally. I mean, you can look at what's here and what's here, and all our values are half as big, other than at 0. And so this results in what we call a vertical shrink. So it's basically, like I said, each point, the y value is half as big as it was previously. All right, so let's go ahead and summarize all this. Notice it says in class we looked at several transformations. For example, the graph of g of x equals x squared plus 2 is obtained by moving or shifting each point on the graph of f of x equals x squared up 2 units. So I've done that on the graph. The following is a summary of the transformations that we have studied. I've included an example of each where f of x is equal to the square root of x. So the square root of x is going to be our parent function. So let's go ahead and look at this. So first of all, let me graph on the bottom here f of x equals square root of x, and you can see how all the others compare. So for example, and then the other thing I would point out again is our function f of x is the square root of x here. So when I say y equals f of x plus c, in our case it would be the square root of x plus some constant. So you can see we have right here, this square root of x plus 4. It's going to cause a vertical shift up 4 units. And let's see, a, that's this one right here. Let's look at the second case, b. Well, we have y equals f of x minus c, so if you subtract a positive number outside the function, it results in a shift down c units. Or in our example, we have square root of x minus 2. So let's see, that would be b, which is right here. So it's the same graph shifted down 2. So these are vertical shifts. In the next one, we have y equals f of x plus c, where x plus c is in parentheses, and this is f of x shifted left c units. An example would be g of x equals the square root of x plus 3. Now this one's a little bit harder to see. Basically, let's see. Whoops, I made a mistake. My c here is 3. Whoops, I'm using the wrong pen. And so you can see that it's y equals f of x plus c, or f of x plus 3. If you plug x plus 3 as an input into the f function, you do get the square root of x plus 3. And so what we're saying here is this is a horizontal shift, and it's a plus 3, so you might think it would go right 3, but it actually goes left. Remember, the horizontal shifts are basically, they work the opposite of what you would expect. And so c, that's right here. Let's move on, or if we have f of x minus c, an example would be, so that would be shifted c units right. So square root of x minus 1 would be an example. That's going to be the same graph, but 1 to the right. So that is graph D. That's actually this one down here. And then here we're looking at a reflection. Most of the time our reflections are going to be through the y-axis, or I'm sorry, through the x-axis. It's going to be this case where you have the minus out front. And so it reflects the graph through the x-axis. So for E, we have g of x equals minus the square root of x, again with the minus out front. And you can see the graph of E is right here. So again, notice we have the original graph, and then if you reflect that through the x-axis, you get graph E. If you have y equals f of minus x, notice the minus x is, or the minus is with the x. It's not out in front of the function. So basically what we have here is y equals f of minus x. Well, since we're dealing with the square root function, we're going to take the square root of our input, which is minus x. And so in this case, the graph, that would be f, and that's this one here. So notice we've reflected it through the y-axis. And then finally, well, we have two more here. We have a vertical stretch. That's this case here. Notice you have a number out front, and a is greater than 1, or this number is greater than 1. It causes a vertical stretch, and an example is g of x equals 2 times square root of x. So that would be this one here. And again, if you look at each of the points on this graph, the y values are twice as big as they originally were. Vertically, the graph is said to be stretched, or it's a vertical stretch. And then our last one, that would be this one here. We have a vertical shrink if a is between 0 and 1. So if you have g of x equals 1/2 times the square root of x, then that's going to cause each y value to be half as big, and that would be this graph here, h. All right, so let's go ahead and practice. We've got 6 examples to do. So first of all, we have several different graphs we can choose from if you look at our basic graphs or our parent functions. So on number 1, our graph is going to be y equals x cubed. And so again, you should know what that looks like. You could easily plot some points if you needed to. And so there's our 5 points that we use. These are kind of the key points in here, pretty easy to remember. They're the same points that you find on the cube root function. So anyway, this minus 1, all that's going to do is cause this graph to go down 1. So let's go ahead and do that. And so there's the graph of f. And, whoops, I'm getting ahead of myself here. So on number 2, now our parent function is the absolute value function. Do you know what that one looks like? Well, it's the V-shaped graph, and it looks like that. Now the minus there is going to cause a reflection through the x-axis, and the plus 2 there is going to cause a vertical shift up 2. And so one thing you should know is we always do reflections or shifts, or I shouldn't say shifts, or stretches or shrinks first. And shifts always come last. All right, so let's go ahead and reflect this through the x-axis. Of course, 0, 0 is on the x-axis, so that doesn't go anywhere. And we'll reflect each of these points through the x-axis. Just graph the point that's the same distance on the other side of the x-axis. And so this graph here is actually y equals minus square root, or absolute value of x. And we're just going to move that up 2. So each point gets moved up 2, and that's our graph. All right, let's move on to number 3. We have the same parent function. Let's go ahead and graph that. Now, if you haven't already started doing this, you might stop the video and try each of these and then watch the video, and or do that as you can. All right, so the minus 2, that's going to cause us, that's a horizontal shift. We're going to go right 2. The minus 3 is totally separate from the absolute value part. That's going to cause a vertical shift. That'll be down 3. So we're just going to take each of our 5 points and move them right 2 and down 3. Now I actually like to move the vertex and then I just draw the same shape. You can do it either way. So I moved the vertex, and now I'm going to draw the same shape. And there's your graph. All right, on number 4, the parent function is the square root function. So let's plot our 3 points for that one. And again, we have, on this one we have a reflection through the x-axis. We're going to go 4 left, that's horizontally, and 2 up, that's our vertical shift. So again, we'll reflect first. So that point doesn't move. The other points we need to reflect down through the x-axis. And so that's the graph of y equals minus the square root of x. And we need to move each of our 3 points 4 left and up 2. And so those are going to be those will be our 3 points for this graph. All right, let's move on to number 5. So the square root function is our parent function. We know that looks like that. So notice because of the 2, we're going to have a vertical stretch. We sometimes say by a factor of 2, which means each of our y values are going to get bigger, or they're going to be twice as big. And then we have the minus 3. That's going to cause a vertical shift down 3. So we'll do our stretch first. So we're just going to double each of our y values here. So we were at 1, now we're at 2. On the regular graph, the square root of x, we were at 4, 2, so we'll be at 4, 4. And so that would be the graph of y equals 2 times the square root of x. But that's not our graph. We need to move that down 3. So move each of those points down 3, and there's your graph. All right. So again, I would encourage you to maybe try this last one before you watch the video. and see how you do. All right, so there's a couple ways you can do this one. First of all, our parent function is the absolute value function. And we've got a reflection through the x-axis. Notice because of the 1/2, we're going to have a vertical shrink. And then finally, we're going to be up 4. Now, we could do this a couple of ways. I'm going to go ahead and do it one way, and then I'll explain what we could have done differently, or a second way to do the problem. So let's go ahead and reflect, because reflections and shrinks or stretches we do first, and it doesn't matter which of those two you do first. So I'm going to reflect it, but then I also need to basically take half of each of my y values here. So like right here, half of -1, we would be at -1/2. And actually that's how it's going to be at each of these points here. And then the next two are down 2, so we'll be at 1 for those. And actually I could have stopped there. I got an extra point there. If I do use that point though, I would be at 1.5 if I went halfway. So I got a little carried away there. I have more points than I really need, but anyway, so here's the thing. I did that in 2 steps to get to the graph that we're at here, this one here, which is really y equals -1/2 times the absolute value of x. So what I could have done is I could have just multiplied each of my y values by -1/2. So here the y value was 1. So to find the point that corresponds to that, I could have just multiplied by -1/2 to get this point here. So you could do it in 1 step or 2. So similarly here, we're at 2, so when I multiply by -1/2, that would be -1, and notice that's where we are here. So you can do it in 2 steps or 1. Either way is fine. And then now we can move the graph up 4. Again, I've got a couple extra points there, and our graph looks like that. All right, that's the end of this video.